Morning, guys. Hope you all are doing good. Yeah, my face is little okay today, so I can show you. Right.
Good morning.
So yeah, good morning, good morning. Right. So we'll straight away start. We have enough people. We have 12 with us, right? Let me share my screen. Yeah, now I can. Okay, fine. Hope you all remember what we saw last class, right? I mean, not this. So we saw, starting with Dalton, we moved on to discovery of, let's just go to that. Yeah, so Dalton, we saw what Dalton said, what are the problems. With Dalton's theory, indivisible was a problem because after some time, a lot of subatomic particles, we call it, whatever is inside the atom, right? So those were discovered. And then the second problem was with isotopes. He said that each atom will have, I mean, if I have an element, that element will have only type, I mean, its kind of atom, and that particular atom will have its own constant weight. Right, so that is not the case with isotopes. They are same atoms, but different weights. All are hydrogens, but or different forms of hydrogen, different weights. And then we went on to see how electrons were discovered. We had the cathode ray tube. All this so much stories were there. The vacuum, like 1 or 2 openings, one for vacuum pump, one for hydrogen gas to come out, and then the power supply was turned on. Something was moving. Now he wanted to find out whether it's charged or uncharged. He found it is charged, and through this experiment, by connecting another extra electrodes, right, he was able to find that it is negatively charged. And then he wanted to find whether it's parted. The cathode rays are made up of particles or waves. So for that, he had a paddle wheel, and he found it was rotating if this cathode rays hit it. And I know, according to Einstein's equation or any other equation, actually, I forgot to mention this point. Not only, Einstein's equation. Say I take kinetic energy. What is this? Some kind of. Okay. So even if I take some kind of handwriting change, I don't know why. Okay, no issues. So anyways, kinetic energy also you take, right? I know the formula is half mv squared, right? So again, you see, if I'm going to have some energy, I need to have some mass. Or even if I take potential energy, I know you know the formula is mgh. Again, you see, mass is a factor there, right? So based on all this, we can actually tell that the cathode rays are made up of negatively charged particles, and then electrons came into the picture. And then he conducted some other experiment also to find the E by M ratios. And then based on this discovery of electron, he gave his own atomic model. He said that atom is a sphere of positive charge, whereas electrons are embedded in it, right? And then then came protons, which was not able to be accommodated into this. And then the position of the electrons were not talked about in this particular model. And then what happened? And then Goldstein, with this modification of the cathode ray experiment, like here I used perforated cathode instead of perforated anode in the previous case. And then he saw scintillations here without a screen, right? And then the only difference was if I use different gases, I got different properties in the case of anode rays, but cathode rays were same for whatever be the gas, either it's hydrogen or helium. I told you, like, it's because here H plus is produced, here He plus is produced. We're talking about the positive charges here, H plus and He plus, or I even say He2 plus if it forms. That is not going to be similar, right? They have different weights, so different E by M ratios will come, right? Okay. Then we went on to see how do you find the charge of electrons, and that was conducted by Millikan's oil drop experiment. So we saw what was happening, and then I told you these two formulas were used to counterbalance the oil drops, and then this value of charge of electron minus 1.6 10 to the minus 19 coulombs was found out, right? And then nucleus, that's where Rutherford came. The famous alpha scattering experiment. We know 3 observations were there, right? And based on that, 3 conclusions were given. The most important one is this deflection by 180 degrees. Obviously, I need to have a very strong positive charge present in the atom so that only strong repulsion will happen. And then the 180 degree deflection can happen. And that very strong positive charge is what is termed as nucleus. And then we saw how the model is: nucleus at the center, protons at the center, electrons revolving around the nucleus, right? And then obviously there were stability two problems. One you can remember, one is stability, the next one is spectrum problem, right? So spectrum problem, what we expect from this phenomena, what he explained is a continuous spectrum, but what we see in reality is a line spectrum, right? And we even saw what do you mean by a spectrum, right? I told you a spectrum is nothing but a collection of energies, collection of points. So you can see this is like a scale. It can be start with lowest energy, high energy, or it can even do in terms of wavelength. We'll speak about the relationship between energy and wavelength in a little more detail. Anyways, so if I say electromagnetic spectrum, this is going to contain all the energy values which are in the range for electromagnetic radiation. So starting with radio waves till gamma rays, all the others are in between, right? And the difference, what do you mean by continuous and line spectrum? I even that explained that, right? If I get only one single value during a process, right? One single line in the spectrum, that corresponds to one single value, that is line spectrum. If I get a range of values, say 10 to 100, then it becomes a continuous spectrum, right? Okay, this is where we stopped last class. Okay, so we'll continue today. If you have any questions, obviously you can ask me from the previous class, anything. 18th. All right, fine. So we talked about spectrum and see till this point, okay, till this point, something has changed in the settings. I don't know what has changed. Oh, this is the, okay, fine. Anyways, so till this point, right, till this Rutherford's, this is so small. Okay, so till this Rutherford's time, right? Okay, so this concept of energy, right, during any process for that matter, right? How this energy transfer happens, all these stuff actually was a very interesting thing. Say, for example, one famous thing, if I want to speak about, I can speak about this black body radiation, right? Okay, now, but this thing is very thick. I don't want to use this thick. Right. Anyways, so first we'll try to understand what is a black body. Okay. Now you must have you must have definitely heard this term black holes. Very fancy term we use whenever this NASA and ISRO people they speak about this black holes. Fine. So a black hole, like basically like I would say a black hole is a type of black body. You can consider it like that. Or I would say black holes and black bodies are exactly same. Right. So what are these black bodies? How do I give a proper definition to this term black body? Okay. So ideally speaking, obviously ideal conditions we'll never get, right? But ideally speaking, a black body is something which can absorb or release any amount of energy. As simple as that. I can all, this is a very apt statement that you can give to a black body, and this is what you will see in any of the literature which you're going to study also. Okay, so a black body is something which can absorb, okay, this is or, okay, or, okay, so an absorb, it can absorb or release any amount of energy. So what do you mean by that? Any amount of energy you throw at a black body, it is going to absorb it. Okay, and whatever energy is absorbed or whatever energy it didn't absorb also, it will be able to release it also in the form of radiation. Okay, so obviously whatever is coming out, right, whatever is releasing, obviously that will be in the form of radiation. That radiation is what is called as black body radiations. Okay, now Newton was the one who actually spoke about, he wanted to see how this energy transfer happens and all that. Okay, so he was like, so this particular statement, like absorb or release any amount of energy, was also given by, say, or not given by, at least inspired by the work of Newton. Okay, so what exactly can tell, like what exactly Newton told is, or if I have to put it in the words in which common people understand, he said that it is going to be a continuous spectrum. Okay, this we know. What is a spectrum? We know, right? And we know what is a continuous spectrum also. Right? He said that it is going to be continuous spectrum. Okay, this is one of the problems. Actually, this is where your Planck, I told you that we are going to speak about this Max Planck. Right. So this guy now came into the picture for this particular thing only. Okay. So he said that it is not actually going to be continuous spectrum, but it is going to be a line spectrum only, right? We'll see how he's going to prove that it's going to be a line spectrum. Okay, this is where actually he came inside, right? This is how Planck started, disproving Newton. Okay, fine. Anyways, what the act, if I have to go into the details of this, how exactly, whatever, like it'll take a lot of time. Okay, but actually I can tell you this line spectrum, how it comes in like when we actually see about the electrons and stuff. Okay, this is just for you to give a quick, a history, a kind of fun fact, to understand like how Newton and Planck got introduced. Okay, anyways, so continuing. So as I told, I already mentioned this. Newton's laws of motion. I know 3 laws of motion. I think you know the equations also, right? Say I have S is equal to ut plus half at squared. V minus u is equal to at. V squared minus u squared equal to 2as. So all these are the 3 fundamental equations of motion Newton told. Okay, right? So we know V is velocity, A is acceleration, S is distance, all these things we know. Say till this point, right? Rutherford said that the electrons will be continuously revolving around the nucleus. Correct, right? So what happened? If they're continuously revolving around the nucleus, they are moving, right? So obviously this the velocity of the movement will have some velocity, it will have some distance, all these things will be there. So if I use these equations, right, if I use these equations, they should actually, correctly coincide with the electron's movement, right? If an electron is moving, and the only equations of motion I have are actually for this, right? So obviously they should be able to, satisfy each other, right? But what Planck found is that it is not actually matching. Okay, it is not actually matching. And I told you that there is this the problem of continuous and line spectrum, right? In the case of Rutherford's model, according to this model, we expect a continuous spectrum, right? But what I see in reality is a line spectrum. Okay, so what he said, right, what Max Planck said to overcome all these problems is, he said atoms are made up of number of elementary oscillators. Okay, right? This is a very famous statement. He said atoms are there. Okay, these atoms consist of so many number of elementary. Okay, this is oscillators. S. Okay, they contain so many number of elementary oscillators. Okay, we know what are called as oscillations. Oscillations are like moving like this, to and fro motion, right? Oscillators are the ones that are oscillating. Okay, so there are so many substances, there are so many number of these which are continuously oscillating, or I can call it as vibrating. I can even tell this. Okay, there are so many vibrators or oscillators present inside the atom. Okay, now when he started this, when he started his research, right, he didn't know what these elementary oscillators were. Okay, he just gave the name elementary oscillators. But when J.J. Thomson, J.J. Thomson discovered electrons, he understood that these elementary oscillators are nothing but electrons. Okay, so he said initially when he started his research, he said that atoms are made up of so many number of elementary oscillators, but he didn't know what are those elementary oscillators until J.J. Thomson found that it was electrons. Okay, right. Anyways, so basically we are talking about electrons here, and what you have to understand is these electrons are continuously vibrating or oscillating. That's what you have to understand. Okay, now if they need to vibrate, right? If they need to vibrate, there should be some energy associated with them, isn't it? Or for any kind of work we do, obviously we know we need energy, right? So oscillation or vibration is also a kind of work, right? So obviously these electrons has to possess some amount of energy. Okay, now this energy, he said, is directly proportional to the frequency of oscillation, the frequency at which the oscillators are oscillating, or I would say frequency at which the electrons are oscillating. What is the frequency? Now, the term frequency is very simple, right? Say in 1 second, how many oscillations you do. For example, in 1 second, I go 5 times, come and like I go and come back at 5 times. in 1 second. That means my frequency is 5. Right. So remember, frequency is nothing but number of cycles per second. You can tell like this. Frequency is number of cycles per second. How many cycles you go 1 second, right? Or if at all you ask the formula of, like, say it is denoted by the letter mu. Okay, this is a Greek letter. You can tell it as mu. Okay, MEW. Okay, so this mu, or they sometimes even they call it as nu. Okay, but anyway, it doesn't matter. This nu is nothing but reciprocal of time, right? Whatever be the time, you take the reciprocal of that, you're gonna get frequency. Okay, right? So what Planck said is that the energy of the oscillation or energy of the vibration is directly proportional to the frequency at which each of these elementary oscillators are vibrating or oscillating. Okay, we now understand what do you mean by frequency. Frequency is nothing but number of cycles per second, or it's also going to be reciprocal of the time. Okay, right. Anyways, so now I have an equation like this, right? I have a connection like this. E is directly proportional to nu, and your nu is nothing but the frequency. Okay, so now it is a very common thing to do in science, right? Whenever you have a proportionality, you include some constant so that this proportionality sign becomes an equal to sign, right? So E, I'm going to introduce a constant called H, right? And this is a, I would say, path breaking. It's a, it's a very big statement, like very big. It had a very influential equation, this equation. Okay, anyways, so this H is what is called as Planck's constant. Okay, this H is what is called as Planck's constant. This is energy in joules, obviously, right? And this is frequency. Now, see, you can understand that the SI unit of frequency is per second, correct? 1 by T, right? So it's per second. Now, this per second is generally called as hertz, and you're denoted by H, is it? Okay, there is the per second unit is called as hertz, and you represent it by H, is it? You must have seen like so many, this frequencies in your radio. If you have used radio, I don't know whether your generation has used it. So in my generation, little it was used, right? So there it written in FM frequencies and all. In terms of hertz only they are given. I think now you can connect all these things. Okay, so the Z is energy in joules, right? And H is the Planck's constant, and this is in frequency, so this is going to be in hertz. Okay, now if you ask me, sir, what is the value of H? The value of H is 6.6 into 10 to the power minus 34 joule per second. That's the unit. You can understand, right? This is joules. This is per second, right? So this will come here. Okay, sorry, joule second, not joule per second, joule second. Okay, that's the, so 6.6 into 10 to the power minus 34. You have to remember this value, people, right? In the exam, they will not give you. Okay, this now, not only this, actually in this particular chapter, okay, you have to remember a lot of numbers. Okay, there will be a lot of constants, not so many, at least say 5-6 values, right? You should be able to remember. Okay, well, this is the first of them. H value is 6.6 into 10 to the power minus 34. Okay, now I told you that this is actually a life-changing equation with respect to science. Why? Because till then, right? Till then, you see, I have told you all the energy equation. E is equal to mc squared. Kinetic energy is equal to half mv squared. Potential energy is mgh. Right? Now you see, all of them had mass dependence. Right? But you see here, right? There is actually no mass dependence. Right? So this is the first time, or I would say, we can understand how in history this happened. First time we can actually see that waves do have energy. This is a life-changing thing, right? Like, I don't know, now it's very simple for us to see, but at that time, see, understand, like a sine wave actually has some energy, like something like that. Anyways, so that's why we said this is a very path-breaking equation. E is equal to h nu. Okay, right. So that is why I wanted to tell about this is that this equation is very, very important. And talking about the line spectrum, right? Okay, continuing on this, right? He said that the energy is directly proportional to the frequency at which it is oscillating. So we can have E is equal to h nu. That's okay. Right. Now he said, say there are going to be so many number of electrons, right? So many number of electrons, each oscillating at different frequencies. Correct. Say I have some 10 electrons, or even say 20 electrons, whatever it is, each of them oscillating at different frequencies. Okay. So if they're going to have different frequencies, they will have different energies. Obviously, right? According to this equation, if this frequency is changing, energy will be changing. So I'll have 10 different value of energies. I'm just giving you some, like random situation, like this is how it is going to be. Okay, so 10 random energies because 10 random frequencies because I have 10 electrons there. Okay, now, like, or if I increase this number to say infinite number of electrons. Okay, if I increase now 10, say assume that I have infinite number of electrons. That means I have infinite value of energy, infinite values of frequency because I have so that many number of electrons. Now, now can I tell the energy values if I just take the range, right? If I just take the range, can I say the energy value will be between 0 to infinity? Whatever values which are there in between this particular range, 0 to infinity, which is basically everything. Is it not? All the possible values of energy, can the electron take and vibrate like that? Is it possible that whatever be the from 0 to infinity, all the possible values of energy can be, what to say, can be held by the electron? Is it possible? All the, or I would say, are all the possible values allowed like that? Is the electron allowed to have any possible energy just because it is going to have some different frequency is the question, right? Now the answer, what he told is no, right? So he said, right? He said there is going to be one elementary oscillator. Okay, there is going to be one elementary oscillator which is going to have minimum energy. Okay, there will be one electron. Why you have to use elementary oscillator? We can say there will be one electron, right, which is going to have some minimum energy. That in all the electrons present, right, that particular electron has minimum energy. Okay, now the other electrons, right, whatever be the other number of electrons, the energy associated with them is going to be based on this minimum value. Okay, based on this minimum value, only the energy of other electrons are decided. Okay, now that seems like a, a complicated thing. Very simple. Based on this, whatever, and I'll tell you how it is dependent. Okay, so what he said is that this minimum energy, the minimum energy possessed by one of the electron is going to have, compared to all the other electron, one electron is going to have minimum energy. Right, now that minimum energy value is called 1 quanta. It's n comes here, 1 quanta. Okay, now what do you mean by a quanta? Quanta means a packet. Okay, 1 quanta. This minimum value of energy possessed by one of the electron, he called it as quanta. And quanta is in some other language. In English, it basically means packet. Okay, 1 packet. Okay, now I told you, based on this minimum energy only, right, all the other electrons' energy is decided. Now, how it is decided is that, say, now this I'll call as E1, right? E1 is equal to h nu 1. Okay, and then this is the minimum value, and obviously this is the minimum frequency, right? And this is my quanta. E1 is my quanta, right? So what he said is that, say n electron, now second electron, now E2, E3, E4, E5, E6, whatever. That means the second electron, third electron, fourth electron, fifth electron, nth electron, En, of that particular electron will be equal to n into E1. Very, very simple. Now this n is nothing but an integer. Right? It starts with n is equal to 1, n is equal to 2, n is equal to 3. It keeps on going. Okay, so now you see the connection, right? There will be some minimum energy, right? And all the other energies of all the other electron must be an integral multiple of this particular value. For example, right? Let me give you an example. Say the E1 value is, say, 5 joules. Okay, right. Now let me ask you. I have 12 joules, 15 joules, 10 joules, 9 joules, 20 joules. Now, these are all the, I'm telling that these are all the possible energy values. Out of them, which are all allowed, right? Tell me 12, 15, 10, 9, and 20. Out of this, which and all will be allowed, which and all will not be allowed. Based on this, I told you.
15, 10, and 20.
Exactly. 15, 10, and 20 are allowed. 12 and 9 are not allowed. Why? Because 15, 10, and 20 are multiples of 5. If I multiply with 3, multiply with 2, multiply with 4, I'll be getting this value, but this value I'll not get. Okay, so you can understand now the possible values of energy of any electron is going to depend on this quanta. Only the integral multiples of this quanta, the minimum energy, are only allowed. No other value is allowed. Okay, that means what? No other energy value can be processed by the electron. Yes, go on. Yeah.
Sir, n cannot be negative.
No, n cannot be a negative value, n cannot be any decimal, n can only be integers, positive integers. Okay. Right?
Okay, sir.
But the energy value itself can be negative. The n value cannot be negative, but the energy value can be negative. We'll speak about it later. How it can be negative or not. Okay, it's a vector quantity, right? Energy is a vector quantity, so it can be both positive as well as negative. We'll speak about it. What do you mean by negative energy or not? We'll speak. Okay. Right. So now we understood, right? So this minimum energy, right, is what is the thing, quanta. So I can now go back to what I started, that is this one, black body radiation. Right now, what this guy said, right? Newton said is that it's continuous spectrum because all possible values, say 0 to 100, if this is the spectrum, entire spectrum will be, blocked in case of a black body. If I'm going to check about a black body, but now you see, not only if at all electrons are the building, atoms are the building block of any matter, right? And inside them I have electrons, right? And the energy of those electrons is, yes, if I say quantized, guys, this is a very important term. When I say something is quantized, that means there should be a minimum value. All the other values are integral multiples of the minimum value. That is what you mean by this term quantized. Okay, again I repeat, there should be some minimum value, right? And all these things should be n into the minimum value. MV is the minimum value. All the other allowed energies or allowed values should be integral multiples. That is what we mean by the term quantized. Okay, so now if the electron's energy is quantized, right? Obviously, that makes up the atom makes up everything, and now a black body is also maybe made up of atoms, right? So obviously, it cannot be a continuous spectrum. It is going to be a line spectrum, and that's exactly what we see also. But it is not going to be line spectrum like, say, how do I put it? Like if I have the spectrum like this, right? I will have one line here, one line here, one line here, one line here. That's it. It's like that. Now, between this, no energy is there. That's what you need to understand. Okay. Now, say this is point A and point B. I have two lines. Please tell me.
Sir, could you repeat how this black body radiation is?
Yeah, coming to that, right? Okay. So what I'm telling is, this is not a continuous spectrum. It is going to be line spectrum like this. Like line spectrum, a little different kind of line spectrum. I will have, say, 4 lines here, right? This is point A, point B. Now this energy, yeah, it is, say, absorbing or releasing E1. This energy is also absorbing E1 or it is E2. But in between this, right, no energy is absorbed or released. It's something like that. Okay, so if I start with 0 to infinity, this is 0 and infinity, there will be multiple lines like this in the spectrum, right? So these are multiple line spectrums, but it is not a continuous spectrum. That is what you need to understand, right? So if I have to put it in one, this thing, a black body is not something which can absorb and release 0 to infinite values of energy. No, it cannot absorb and release any amount of energy, right? Now, from 0 to infinity, there are so many values, yes, right? But all these values are going to be multiples of this particular value. Okay, that is what we need to understand. When I say it's quantized, right, the black body radiation is also quantized, means it is exactly going to be a line spectrum only. It is not a continuous spectrum. And all the other values of energy or the wavelength or whatever it is going to be dependent on this particular smallest value. That's exactly what happens in case of a black body radiation also, right? And if at all you ask me, what is black body made up of and so on and so forth, even scientists are still working on that. Okay, right? So any other questions anybody has in this particular area? Right, I hope everything is clear. Right, the concept of line and continuous spectrum is very important. The concept of being quantized or quantization, all these things are very, very important. Right, what do you mean by quantized? Basically, the process of converting something into a quantized quantity is what is called as quantization. Right, and okay, all these are very, very, very important. Okay, because why these are important? Because once again, sorry guys, there's a small thing I had to take care. So yeah, so everybody understood what do you mean by quantized and why this particular equation is very, very important. E is equal to h nu. Why is it so important? I think everybody understood, right? Or I can even write this equation as E is equal to nh nu. Right, that makes sense, right? There'll be some minimum frequency and h is a constant, so nh nu will basically what, n into e1. That's what the e1 is equal to h nu, like that. Right. Okay. Anyways, moving on. Now, why it was so important at that time is because based on this, right, based on this quantum theory, it's called Planck's quantum theory. Okay. Now, based on this Planck's quantum theory only, the entire Bohr's atomic model was based upon this. Right? Based on the Planck's quantum theory, right? The theory of quantization, right? Based on that only, Bohr's atomic model was built upon. Okay, fine. We'll try to understand what are all the postulates, right? Where first we'll try to understand what are all the postulates of Bohr's atomic model or Bohr's atomic theory, however you want to call it. Okay, fine. He said he said electrons, right? The main problem with other theories were that the position of the electron was a problem. Is it not? Right. So he said electrons are there in some place called as stationary orbits. Okay. He said that electrons are there in some place called as stationary orbits. Okay. He just gave a place. Right, and these stationary orbits are circular in nature and circular in shape. Right, these stationary orbits are circular in shape. They are circular. Okay, fine. Now, what are so special about these stationary orbits? Okay, what are so special about the stationary orbits? Or if I have to put it in other words, the electrons, I would say, revolve around the nucleus in these stationary orbits. Okay, it's very simple to put it like this. Say they assume that this is the nucleus, right? And this is one stationary orbit. Okay, and another, this is another stationary orbit. Okay, so only in these stationary circular orbits, the electrons revolve around the nucleus. That's what you need to understand. Okay, these are circular in shape. This will be the center. First stationary orbit, this is n is equal to 1. This is n is equal to 2. Okay, third stationary orbit will be again beyond that. It keeps on going, and these are circular in shape. That's what you need to understand. Okay, now the same question will come, right? So if they're going to move around the nucleus, right? If they're going to move around the nucleus, right? They should spend energy, right? And if they spend energy, they'll eventually lose all their energy, correct? And they'll eventually fall into the nucleus, right? So how these stationary orbits are going to help in those situations? How is that the stability of electron is still maintained? How? With the help of the stationary orbits. Okay, so for that, he said that the stationary orbits are special, right? Because if the electron is going to be in its own stationary orbit, now please understand, even though we all are humans, right? We all have our own homes, right? You have your home in Velachery, I have my home in Mylapore, right? So like that, even though all of them are electrons, right? All these electrons will have different homes, or in the sense that they will have their own stationary orbits. Okay, now as long as electron stays in its own stationary orbit, electron in its own stationary orbit, I call it as SO, right? If it stays in its own stationary orbit, now it is not going to lose energy. No loss of energy. No energy is lost. Okay, even though it is moving, right? So something is so special about the stationary orbit, right? As long as the electron stays in its own stationary orbit, even though it is moving, it is not going to lose any energy, right? How? I'll tell you. Like maybe it comes in the derivation. Not we don't have to see the derivation, but how is it that the electron doesn't lose energy as long as it stays here? We'll see. Like I'll give you a little insight about this. Right? What is the magic there? Okay, right? Fine. So that is what is special about the stationary orbit. Okay. Now, third thing is that, I mean, obviously he said that the third point was that he actually said that the station orbit is circular in shape. Okay. So moving on, after that, what he said the energy of the stationary orbit, all stationary orbits, energy of the stationary orbit means obviously energy of the electrons in these stationary orbits. Okay. They are quantized. I think now you can understand what you mean by quantized. Obviously, there will be the first stationary orbit, right? It will have some energy, right? Now, the second stationary orbit will have energy of 2e, and the third stationary orbit will have the energy of 3e, and the fourth one will have the energy of 4e, like that. Okay, that is what I mean by the energy of stationary orbit being quantized. Now you can understand what is the connection between your Planck's quantum theory and your Bohr's atomic model. Okay, so he said that the energy of the stationary orbits are quantized. Okay, now what other things he said? Let me recall. I think these are all the important points, I guess. Okay, so anyways, these are all the important points. Okay, last important one more thing is there. He said the angular momentum. This is also a very important stuff, right? The angular momentum is also quantized. Okay, the angular momentum is also quantized, right? Okay, now what do you mean by angular momentum? Or I don't want to go into the physics of it, but I can give you the formula for angular momentum. Now I know momentum is mv, right? P. Momentum is P. Momentum formula is mv, right? So whenever any of this angular term comes, so have they started rotation mechanics for you guys in physics? Have they started rotation mechanics in physics 4th or 5th chapter, I guess? Did they start it for you? Oh, they didn't start. Okay, anyways, you'll study about whatever I'm going to tell in that particular chapter. I'll just give you an introduction. Okay, so whenever this term angular momentum, angular velocity, angular displacement, angular force, like whatever linear terms you have, these are all linear terms, right? For the straight line motion, we say force, displacement, velocity, acceleration, all that. Now, that's when I have circular motion, when I have rotation, now there comes the term angular momentum, angular velocity, angular displacement, something like that. Okay, so now remember the linear term into radius will always give you the angular term. Okay, whatever be the linear term, you multiply it with the radius, right? You are going to get the angular term, but it will not hold good for all the angular terms, but yeah, for most of the angular terms, this will hold good. Right? So if momentum is mv, right? Angular momentum, AM I call it, right? Angular momentum will be is equal to M into V. Now I have, if I have to multiply it with R, it becomes MVR. Okay, that's the formula for angular momentum. Okay, so he said that angular momentum is, first we'll see, angular momentum is formula is MVR. MV is momentum into R. If you multiply, it becomes angular momentum, right? Okay, now he said the angular momentum of electrons are quantized. Okay, so how is it quantized? He even gave a formula for that. This again is a very little important formula. MVR is equal to NH by 2 pi. Okay, he said that is quantized. You can see the number N, and N is again an integer. Okay, MVR is equal to NH by 2 pi. Okay, right? That's the formula you need to understand. That's it. Okay, H, you know the value. Pi is 3.14, 22 by 7. N value is an integer. So obviously H by 2 pi is the minimum value. If I put N is equal to 1, all the other values of what is this angular momentum are quantized based on this integer value. Okay, right? So yeah, these are all the postulates that Bohr said. Okay, now obviously you can understand how the model is. Electron at the center, sorry, nucleus at the center. Electrons will have their own orbits and they will be revolving around the nucleus. Okay, right. Now this is maybe this much you not, I mean, at least say 80% of whatever I told you now you might have studied in your 9th class in atomic structure chapter. Okay, now after this, what we're going to learn are a little more technical, not technical, like this is the overall theory, that's theory is over, right? So in this, there are certain calculations he did, right? He calculated, say first one, he calculated what is the radius of the nth orbit. Right, I know that I have so many stationary orbits, right? Okay, now he wanted to know what is the radius of the nth orbit, right? Okay, Rn. Obviously, if you know the radius of the nth orbit, I will know what to say, where the electron is present. Correct, right? Say if at all the second shell, I know where the what is the radius. I know in that particular circle, anywhere the electron can be there. Right. Okay. So now there is a derivation for all of this, guys, but we don't have to go into the derivation because nobody is going to ask you, right? But the derivation starts with the answer to the question of this. Where is it? Yeah, as long as electron stays in its own stationary orbit, right, it is not going to absorb all of this derivation. Like whatever derivation, I'm going to give you some whatever equation. It comes from a derivation. The derivation starts with the answer to the question. Okay. Now I don't want to go into the derivation, but I can just tell you how is it. Right. See, electron is there. Okay. Now it should move, but still should not lose energy. It should not be losing energy. Now, how is it possible? Now you understand, I would say that electron is in uniform motion. The electron is in uniform motion. Now, what do you mean by uniform motion? You understand, right? You have constant velocity, one particular velocity through the entire circle, only one velocity is maintained. That is what is called as uniform motion. Okay, now you can understand. So if at all you go to Newton's second law, okay, you go to Newton's second law, right? What it says? As long as as in uniform motion. 1 second, I'm getting confused, I guess.
Sir, Newton's first law, inertia.
So what it says that as long as this thing is at rest or uniform motion, it will there'll not be any force. What exactly is the statement?
So
Anybody remember Newton's first law?
Object continues to remain in rest unless and until an external force is applied on the object.
Okay, fine. Thank you for making me remember. Right, so it is going to be at that particular state of rest or in the uniform motion as long as any external force acts on it. Okay, now only if external force acts on it, guys, then I will have energy. I think you know the relationship between energy and force, right? Energy is equal to F dot ds. I mean F into force into displacement, if I have to call it, right? So only if I have some external force acting, right? Only if I have some external force acting, then there'll be some amount of energy absorbed or released. That depends on the phenomena. That depends on what is the situation there. Okay, so if at all I make this force 0, obviously the energy will become 0. That is the whole idea here. Okay, now the electron has to move. So if we can make sure that the electron is going to have uniform motion, right? If I can make sure the electron is going to have uniform motion, even though it moves, it is not going to lose any energy. That's the part. That's the catch here. Okay, if I'm going to have uniform motion, there is no loss of energy. As simple as that. Okay, for me to have no energy, for me to have uniform motion, the external force, the total force acting should be 0. Only then the energy will be 0. Right? Okay, now when something is moving, right, when the electron is moving, it is obviously not that the force is like, we can see, first we'll try to understand what are all the forces actually acting on the electron. Can you tell me if the electron is moving, right? Can you tell me what forces are acting on it? Remember, like, remembering there is nucleus,
Centripetal force.
stuff. What force?
Centripetal.
Okay, because it is moving, right? Okay, yeah, its centripetal force will be acting on it, right? And because it is circular motion, the next force, there's one more force is acting.
Electrostatic.
Yes, absolutely, right? There is still electrostatic force acting between your nucleus and the electron. Okay, so I have Fc, I call it F centripetal, and say Fe, I call it. Okay, now if I can make sure that Fe and Fc are equal, because those two are the only forces acting in opposite direction. This will be in this direction, this will be in this direction. So now what happens? The net force will become 0. If the net force becomes 0, the E will be 0, then obviously it is going to have uniform motion. And that is how, if the electron stays in its own stationary orbit, right, its centripetal force and electrostatic force will be balanced so that it doesn't lose any energy. It's as simple as that.
Sir?
Yeah, please tell me.
Sir, using this logic, if Rutherford could have said that all the electrons are moving in a uniform motion, so his model would have been correct, right?
Yeah, but see, if I have 10 electrons, right? Now 10 electrons will have 10 different orbits. So they will have, yeah, uniform motion alone shouldn't have been sufficient. He should have told where the electron is present also. That also if it would have included, yes, it would have been a correct model. Right? Uniform motion plus the point that it has some place where it can stay or it can rotate. That also if it have said yes, his model would have been correct.
Okay, sir.
Right. Fine. See, why am I stressing this point? Yeah, please tell me.
Sir, the electron revolves in circular motion, right?
Yeah.
So when it is revolving in circular motion, so velocity isn't going to be same because direction is continuously changing.
Correct, obviously, correct. The direction is continuously changing, yes.
Then how is it uniform motion?
Oh, see, circular motion need not be uniform. Okay, your question is valid, but you see, when I have uniform circular motion, there is something like that. Okay, uniform circular motion. How I can put it in the way, like you'll again study this in your rotation mechanics, but I have to put it in some way in which you understand. You understand that it is constant angular velocity. Okay, if I have to specify that point, then only maybe it's fine. I have to stress the point that it is constant angular velocity. On the constant angular velocity, it keeps on, that is how it maintains constant uniform motion. Okay, now you understand, obviously the direction keeps on changing. Okay, now if the direction keeps on changing, that's okay. This is also a vector quantity. Okay, but the velocity's direction, right? The direction of velocity keeps on changing. Okay, but the direction of angular velocity will be remaining constant. If I have to, if that's what you're asking.
Okay, sir.
Right, yes, understood. Sir. Right, good. Right, that's
yes,
a good
sir.
question actually. We'll study more about in detail. You'll study about in your rotation mechanics. Okay, right. So yeah, so making sure that these two forces are equal, I can make sure that the electron doesn't lose energy. Okay, now why am I stressing about this home part? Each electron should have its own stationary orbit, is because when the electron is not in its own stationary orbit, but say it is going to be in someone else's home, say some other stationary orbit than its own stationary orbit. Now then it is going to have some energy energy lost or energy gained. Now please understand. Now if the electron shifts from lower to higher stationary orbit, say it goes from first level to fifth level, right? Now please understand that the energy will be absorbed. Energy will be absorbed. Now why? You can understand it easily. Say now this is E, the first orbit. Second orbit will have 2E, right? Third orbit will have 3E, right? So what do you understand? When you go from first, second, third, fourth, if you keep on going, the energy of the orbits are also increasing, keeping on increasing, right? So obviously the electron here would have had very less energy. So if you supply some energy into this, now the electron can go to the third level or fifth level, depending on what energy you supply. Okay, so whenever the electron wants to go from lower to higher level, right? And obviously it has to absorb some energy. Okay, and obviously the opposite fact, when the electron comes from higher level to lower level, right? Energy will be released. Right? Energy will be released. Okay, right? Fine. And now this you understood. What is the time? Okay, 5 minutes. Now this you understood, right? Energy absorbed and energy released. All these things you understood. Now I told you that energy is a scale, vector quantity, so it will have positive and negative values also. Okay. Now please understand, people. Whenever, not only here, from all the things you're going to see till now, right? Wherever this kind of energy is coming, whenever you see that energy is absorbed, it is going to be a positive value. Okay. Whenever energy is released, I give it a negative value. If, for example, I tell that 5 joules of energy is absorbed, then I will tell that the E value is +5. Right? Now, if I tell that 5 joules of energy is released, then I will tell that the energy value is -5 joules. Okay, this you can remember. Always this will work, right? Especially in thermodynamics. Okay, when we go to the chapter 4th or 5th chapter, which we'll see, this and all are very, very important. Okay, energy absorbed should be given a positive value. Energy released should be given a negative value. Right? Okay, fine. So now we understood why is it that, when the electron own orbit is second orbit, right? But if it is in first orbit or say fifth orbit, definitely it will absorb or lose energy. Now you can understand why. Say if it is going to go from second to first orbit, right, it is going to release some energy, right? Now if it goes from second orbit to fifth orbit, energy is going to get absorbed, right? So, but as long as the electron stays in its own stationary orbit, nothing is going to happen. Okay, right? Fine. That is the thing about stationary orbits. Okay, now I just give you the formula for radius, because we started it, right? Radius of the nth stationary orbit, right? The formula goes like this. It's 0.0529 angstrom units. Oh, wait, I'm so sorry. Right? 0.0529 N by Z angstrom. The unit is angstrom. Now, please understand, angstrom is 10 to the power -10 meters. Okay, 1 angstrom. I write 1 angstrom is equal to 10 to the power -10 meters. Okay, now this N is which stationary orbit you're talking about. N again can be 1 for the first orbit, 2 for the second orbit, 4 for the fourth orbit. Okay, and this Z talks about atomic number. Okay, for example, for hydrogen it is 1, for helium it is 2, for lithium it is 3. Okay, so Z is the atomic number of the element which you're talking about. Okay, this is the formula. Rn is equal to 0.0529 N by Z. The answer which you will be getting will not be in meters, it will be in angstrom units. Very, very important. Okay, right? Very simple formula. Yeah, please tell me.
Sir, it's an unrelated doubt, but does the proton of one element weigh the same as the proton of another element?
Yeah, sure. One proton weight, irrespective of whatever be the element, it is going to be same. One proton's weight, yes, it is going to be same.
Okay, sir.
But then obviously, like two elements cannot have same number of protons. That is how basically the entire periodic table is defined, right? Periodic table is the main from your 10th class. If I have to use the correct term, the reason for periodicity, right? It is actually the atomic number, because two different elements have two different atomic numbers. That is why they're two different elements. It's like that, right? So basically, if I have same number, I can have protons weight to be same, right? One proton's weight to be same, but no two element can have same number of protons. Like that's the beauty of it. That becomes an atomic number, right? Okay, fine. Okay, I think we'll stop with this for today. Okay. Is there any other question you want to ask me? I hope everybody understood what we saw. Yeah, actually, I forgot to tell you. Yeah, exactly. I was about to tell that. So this class is still only till 12:30 today. Okay, because I already told them that no, I thought I'll not be taking this class, but I thought already one class was missed, so I don't want to waste this class also. The class today is only for 1 hour. Okay, because yesterday itself I told you that this still I'm not 100% feeling good. Okay, so now one more thing I want to tell is by coming Friday, okay, you will have another extra class. See, we missed one class last Sunday, I guess, and then today half an hour we are missing. Okay, so by coming Friday, you will have an extra class for 2 hours. On Friday, extra class for 2 hours. So don't worry, you don't have to sit for 2 hours continuously. So 1 hour we'll have class. I'll give you 15 minutes break. Again, I'll have 1 hour class. Okay, so remember that by Friday, we'll have a 2 hours. Yeah, please tell me.
Sir, I didn't understand how E by M ratio is not constant in case of protons.
No, E by M ratio, if it is proton, it is same. But what you have to understand is that it is not protons which are causing the scintillations. Please understand. It is not exactly the protons. It is actually the elements' cationic form. Say it's H plus, He plus, or He2 plus, or lithium 3 plus. These positive ions are the one which are actually causing the scintillations. Correct? Okay, so if it is only proton, yes, all the E by M values will definitely be same, because proton is a proton. One proton, obviously the mass will be same, E by M ratio will be same, but it is not the proton. That's the point. It is the entire ion which is responsible for the scintillations in the certain screen. Okay.
Sir, could you please repeat, sir, like ion?
See, now we told that this is the anode part. Sorry, this is the cathode part, right? So I'm going to have some scintillations here because the anode rays are going to come and hit this, right? Okay, now what are these anode rays made up of? Now I told you that H2 will give 2 H plus ions and 2 electrons. Basically the cathode rays are this, no problem, 1d electrons. Okay, now in case of if I use H2, I'm going to get H plus ion, correct? But if I use helium, say I will be getting He2 plus 2 electrons, right? Now this H plus and He2 plus are going to have 2 different masses. The mass value are going to be different, right? And these are the ones which are responsible for the scintillations here. The anode rays are made up of H plus ions in case of hydrogen, and the anode rays are made up of He2 plus in the case of helium gas use. And that is why I said the E by M ratio.
He2 plus, sir. Should be He
While
plus,
H,
right?
yeah, it can be H plus also. Obviously, why not? It can be H plus also, but He2 plus is more stable than He plus. So there is more probability of forming this than this. Okay. Anyway, so what you have to understand is even though I have He plus and H plus, still their mass will be different. That's why you have to understand. Okay. Hope you understand.
Yes,
Right. Good. Yeah. So guys, we'll stop with this for today. So remember that next week we have Friday 2 hours of class. I think I'll stop here. Yeah. So Friday we have 2 hours of class. So the timings we'll get to know. Maybe 5:30 to 7:30 or 5 to 7, something like that we'll have. Okay. Right. Fine. Thank you so much, people. If you don't have any other questions, we can stop right here. Is there any question? Okay, fine. Thank you so much, people. We'll again meet on Friday.
thank you, sir.
Right?
Thank you, sir.